and how to actually integrate Qt for MCU, how to build an application with Qt for MCU, more complex application than the typical example that are provided with Qt for MCU framework. So a bit about me. So I'm a software engineer, I have 12 years of experience. I'm primarily focused on C++ and Qt development. My credentials are that I've actually ported Qt for MCU for various STMs and NXP boards. And the boards that we will be talking about today, which is NXP 1170. So my team was involved in actually implementing Qt for MCU support for this board and providing FreeRTOS support for this board as well. You can reach me under Bartosz Taczala at siili.com or Bartosz Taczala at Qt.io. And I've included my GitHub link for reference. So what we will today discuss, we'll try to figure out how we could use Qt for MCU to build complex application on top of FreeRTOS. We'll try to offload some of the tasks to the secondary core. So we will have we have a board which is NXP 1170, which has two cores, M7 and M4, and we will try to run Qt for MCU on M7 core, and then try to run some parts on M4 core. So utilizing secondary core can be useful in order to either move safety critical tasks or offload some heavier computation that could affect UI smoothness. We will briefly talk about inter-CPU and inter-task communication. We will try to receive the data from M4 core on M7 and then display them with Qt for MCU. Why? Why we would want to utilize a secondary core. So one of the reasons might be a functional safety. So Qt for MCU, or Qt for short, is not certified to use in safe environments. And as well, so FreeRTOS is also not certified. So what we could do is we could leverage secondary M4 core and run our safety critical tasks there and get it certified, but still have Qt for MCU for all the niceness and the graphics on other core. And other reason might be to actually offload some tasks to the secondary core. We may have a computation heavy task, or we may have a task that may affect our UI smoothness and responsiveness, and we could actually leverage the secondary core to actually offload some tasks. As I mentioned, this talk is based for NXP 1170, but we successfully run similar architecture on other similar solution on other architecture, like Xilinx R4A53. So a quick overview of our system this is a screen that comes from Qt documentation. So we have a Qt application. Qt application actually runs on a M7 core, which is very powerful core. And then we have our backend application that runs on a secondary core. The application are synchronized or communicates via shared TCM memory. I will talk about this a bit later on. That uses internal memory that's accessible from both M7 and M4 cores. So we will use this memory to actually exchange data back and forth. So on M7, so our M7 core will contain two tasks. One task is a UI thread, sort of that will present the data from the other core, and other task will be used only for communicating between two cores, right? So task one will display UI, and task two will actually get the data from M4 and pass the data to task one. So the task will communicate between each other. So in this example, I've actually will be accessing data from task one from task two. And this is done for simplicity. We could either use FreeRTOS message buffer or any other synchronization or inter-task synchronization mechanisms. But with this presentation, I will just access the data of other tasks. On Cortex M4, we will have only one task, and this task will periodically send data via the shared TCM memory. So for sharing the data, we will use NXP RPMSG framework. So this framework is based on memory being accessible from both core and on interrupts. It has a nice C API, so we don't have to think as much about how to actually use that. So in the example, I will go through how to actually use that and explain why this is easier than using shared memory and interrupts by yourself. And we will also use NXP's MCMGR. So this is a framework that we can use to actually start the older core and monitor its activity. Then one quick note is that task number 2 will use blocking API for receiving data. So if data is not present, the task number 2 will block. And if data is available, then the task number 2 will notify or will actually change the data for task number 1. There is also an asynchronous API version, but for simplicity, we will use synchronous one in this example. So our structure. So since Qt for MCU uses CMake build system, so we'll use this as well. So we have 2 main directories, which is core big and core small. So core big will contain everything that's associated with Cortex M7, and core small will have an executable that will run on Cortex M4. So the root CMake file is very simple. It contains two functions add subdirectory, and that's all. Core big CMake is a little bit more complicated, right? So we will add a directory UI, and the UI that subdirectory will contain our QML and only our QML file, sorry. And then if we are building for NXP 1170, it will add a directory called communicator, and the communicator directory is a task 2 implementation. So our UI CMake file is very simple. It's find package Qt for MCU, Qt for short. We are adding executable big core, and we are specifying that the executable contains of 1 QML file, and that's it. We are also invoking app target setup OS. So this will automatically pick up FreeRTOS, and we could use FreeRTOS in our application. And we obviously need to link against Qt quick ultralight libraries. The communicator CMake file is a slightly more complicated. It contains of CPP file that will actually hold the task implementation. But we also need to include some other things. So inkbin.s is right now not important. It's this file will be used to storing the data for core M4 core. And since we would like to use NXP's MCMGR and RPMSG, we have to include those. Include those files in our build system. So we have to add them manually, right? So this is a list of files that needed to be added in order to use RPMSG and MCMGR. Yeah, and this is also the rest is also. I will explain later why this is for, but it needs to be here. How can we build our software? So building is really straightforward. So we need to specify where is our ARM GCC compiler. We need to specify where is our 1170 SDK and where is our 1170 FreeRTOS implementation. Once this is done, we are invoking CMake as in documentations, specifying that the toolchain file is ARM GCC. We are building for 1170, and that's pretty much it. Other than, of course, specifying that our operating system is FreeRTOS. Right, so to the implementation. So our M7 core implementation is very easy. So our main file consists of platform initialization, Qt platform initialization, and then creating Qt for MCU task and creating communicator task. And that's pretty, yeah. And obviously we have to start scheduler, start FreeRTOS scheduler. That's it. So our UI task implementation is also simple. We have two global variables, which is our main view item and our application. And in our QL thread function, which will be invoked by FreeRTOS, we are specifying that the root item for our application is root item, and we execute our application. And one thing that we need to note, we need to remember of this function is that up.exec never returns, so it will loop infinitely. And the reason why those two items are marked as global and not within the function are actually to save stack. One of the reasons is to save stack, and the other reason is so that we can actually access them from other tasks. And our QML implementation is very simple. It contains of two rectangles and a text item, and you will try to update this text item text property from the data from M4 core. Our communicator task looks slightly more complicated. So in this task, as I specify that the API that we'll use, RPMSG SBI, will be blocking, we will have a function that reads the data or waits until the data are ready. And when the data are ready, we read those data. Once the data is read, we will invoke on a text property of text item a function called set value. So we will try to update our content, QML content. So this is where it gets tricky. So there is a small bug in Qt for MCU that is being worked on as we speak. And if we invoke the set value with the new data, the item may not necessarily be updated or refreshed on the screen. The value itself is updated, but Qt doesn't know that it needs to be refreshed on the screen. So in order to actually make this force Qt for MCU to refresh that, I've implemented a small trick where I change the current width of the item. And I constantly add one or subtract one from the width so that I'm sure that Qt for MCU knows that the item needs to be refreshed. So this is how I implemented that. But once the bug is fixed, we could simplify our implementation to just call set value and then do task yield. Or Qt for MCU documentations also specifies how to actually interact between C++ and QML. So once this is we have this out of the way. So now we will have to set up our PMSG, and first we will do that on M7 core, and then we will do that on M4 core. So on M7 core we are using MCMGR as I specified to actually start other core, and we are calling MCMGR init, so we are initializing the framework and we are trying to register an event. So we will wait until an event from other call will happen. Then we are calling MCMGR start core. All those parameters will be explained. The most important parameter is the one here. So this is our address where our this is an address where our RPMSG buffer is. So RPMSG buffer is a part of memory that is actually shared between two cores. And in this memory region, we will write data and read data from. Then we have while. So we are waiting until we receive confirmation from the other core that it has started, and once this is done, we are creating our RPMSG buffers. So our data ready implementation is very simple. We are just calling receive or RPMSG, and we specify where is the remote address. where we have to store our bytes in MSG, and what's the size and what's the actual length that we read from the shared memory. Okay, so this was rather simple. So now moving to M4 core. So M4 core is slightly more complicated because in M4 core we don't link against Qt for MCU. So we have to set all the flags and all the macro definition for the compilers ourselves. So as with the communicator task, we are adding executable, which is small core. We have to explicitly specify where our RPMSG implementation is and use that in our project. I've omitted the drivers and the startup initialization code here, but it also needs to be here, right? So this is not the case for M7 part, because on M7 part we are linking against Qt for MCU, and Qt for MCU on 1170 includes everything we need, including drivers and startup initialization code. This is not the case on M4, right? Because we don't link against Qt for MCU on M4. So we have to do that manually. So we have to specify that we are building for 1170 CM4. And then we have to specify that the CPU that we are building is M4. We have a float ABI, a hard float ABI. Our FPU is also specified. And the same goes for linker, right? And one thing that we also need to remember in linking is that we have to specify our linker script for this one. For M7, we didn't have to because Qt for MCU provides default for us, which we could use, but for M4, we have to do that manually. Okay, so our main implementation or Cortex M4 is also rather easy. So immediately after we are entering main, we initialize MCMGR, and then we received startup data from MCMGR. And startup data is the address of RPMSG buffers, right? Once this is done, we could start RPMSG buffer remote session, right? And we use the startup data parameter that we've received from MCMGR, and that's why we are sure that RPMSG buffers are the same on M4. RPMSG buffer address is the same on M4 and on M7. After that's done, we are triggering MCMGR event, meaning is notifying M7 core that we actually have run, and we are ready to go. Sending the data on MC or on M4 core is very easy. We create an endpoint and we just send the message data that we specify. So that's pretty much it. Now we will have to figure out how we can actually embed the binaries together, right? So NXP 1170 allows us to flash M7 core, but what we could do is we could embed the M4 core binary in M7 core binary, and then once the binaries are combined, we could from M7 core copy the data to M4 core and start, right? So how to do that? So as you remember, there was an ingbin.s file that actually does this. And also one thing worth noting is that I've manually added a dependency. So our big core has to be built after small core, and this way CMake will actually correctly embed the binaries, the binary of M4 into M7. So this is our in-bin file on the left. So as you can see, we have a section called M0 image start, which includes file small core bin. Right, so this is small core.bin is an artifact that we've received from building M4 executable. So we are embedding that in MO image start in a section MO code, right? And before actually starting our core, we need to memcopy our binary to where core 1 expects the executable to be upon startup, right? So we have a defined core 1 boot address, a variable that points to an address where the binary should be stored, and this address is received directly from NXP documentation. And we need to slightly modify our linker script for M7. We need to specify that we have a special section MO code, and this special section has to be in the memory M1 core M core 1 image, and it's defined as in here, right? So with this, we have our binary embedded M4 binary embedded in our M7 binary, and right before we start M4 binary core, sorry, we are flashing, or we are copying the binary to where the core expects the binaries to be. Okay, so this was very simple example. So some things that we could consider is we could actually, so the M4 core part was implemented or on bare metal. We didn't use any operating system. Actually, we could use either FreeRTOS or SafeRTOS. So with FreeRTOS, we could actually leverage FreeRTOS message buffer to exchange data not only between task 1 and 2, but we could also use that to exchange data between cores, M4 and M7. So we could actually create a message buffers and exchange data without RPMSG. Yeah, and obviously we could use SafeRTOS or any other any other operating system that's useful in safety critical environments. We could obviously extend the example and use a FreeRTOS message buffer to exchange data between tasks, UI task and communicator task, but this is slightly more complicated as it requires some changes in the Qt4MCU framework right now. What we could do to simplify the architectures, we could actually remove task number 2, which is communicator task, and use non-blocking RPMSG API and QL itself. And that way, on M4 we would have only one task, and on M4 we also would have one task. And since the example in this example, I actually used M7 core to actually initiate the message sending and flashing M4 core. We could actually try to use a different approach where M4 is the master core and M4 has a binary that that has to be flashed on M7 core. And in this scenario, M core would be a master in this communication, and the M7 would be slave. And if we really want to achieve functional safety, we could obviously utilize M4 core as a watchdog monitor, where we periodically send heartbeats from M7 to M4. And if heartbeat is not received or it's slightly delayed, we could actually react in whatever way we see fit. So that's it from me. And I think we have some time for questions right now.
Yes, we have some questions already waiting.
Yeah, QA. Okay.
Yes.
Yes. Okay. So so the first question is: does the described application fit an internal 2 megabyte SRAM or NXP 11 on external memory has to be used? So external memory has to be used in it. So and this is not necessarily this example requirement, but if we would like to use if we would like to store any graphical assets in here, so Qt4MCU has a very nice optimization of graphical assets, but typically 2 megabytes of internal memory is not enough to fit the code and the internal and the graphical assets. So in this example, we could actually fit everything in internal memory, but NXP 1170 implementation by default uses external memory because we wanted to provide a memory bank for a user where they can store graphical assets by default. So are those? So the next question is: are those example files available on GitHub? Yes, they are on GitHub. They are in my private repository for now, but I plan to make them public right after the speak. So they will be available. I've included my GitHub account link, so this will be in my GitHub account link. Okay, so the next question is how you ensure both M7 and M4 are both looking at the same address of the shared memory. So this is this was actually so let me go to the slide if I can. Okay, so if when we start in core, we are specifying a parameter that we can pass to the other core, and this is this RPMSG Lite base address. So this is an address. And then we are passing this address to the M4 core, and on M4 core we are using this method called get startup data, and this startup data is storing this exact address that we've pointed to M4 core. Okay, so the next question is what is the environment you used in the demo? So the environment we used in the demo is, yeah, so I used a typical Qt-MCU SDK, and yeah, and the environment is, so, yeah, okay, so that's probably not the case. So I used Linux. This is not supported in Qt-MCU right now, but I think it's planned to be supported and planned to be released for a public, right? But this is so. But since we are cross-compiling, we could replace that. We could easily replace that environment with Windows-based SDKs. Okay. Next question is: can it be implemented for i.MX 8 family, where we have A53 and M4 core? Are those examples available in Qt distribution? So okay, so those examples are not available in Qt distribution yet. They will be available on my GitHub page. So the question about i.MX 8 family is that we would have to actually port Qt-MCU on i.MX 8 family. And A53 is a core that's more suitable to run full Qt rather than Qt-MCU. So on other similar platforms, what we actually did is we ran Qt-MCU on M4 core, and we did some data exposition out of A53. So M4 core was actually responsible for displaying the data, and A53 was responsible for providing the data. But the similar architecture is possible on other cores, provided that they have shared memory implementation. Okay, so the next question is: can you please demonstrate this example on the target? I would love to do that. I really do. However, NXP 1170, the boards that we have are challenging to work with. In the sense that flashing is not consistent. So if I have a big enough example, the flashing sometimes fails, or sometimes doesn't fail. So it's very difficult to make this training session as I planned, or as I originally planned. Okay, so the next question is: an interaction to a touchscreen also possible? Yes, Qt-MCU actually implements or actually supports Qt touchscreens. So if we are running Qt-MCU on M7, we have on NXP 1170 M7 core, we have full touchscreen support. The next question is about other operating system like AutoZAR. So there is an investigation going on in Qt-MCU about other operating systems. So right now we've released or Qt released preliminary FreeRTOS version, but other operating systems are also being looked at. Next question is: can those examples work on an XP device like STM32? So this is so I would say yes, but we would have to replace RPMSG and MCMGR with something that STM provides, right? So So in this example, Qt for MCU doesn't necessarily know anything about RPMSG and MCMGR. So this is so it's kind of Qt for MCU is agnostic in that sense. But if we provide something similar, or if STM32 provides something similar on their boards, then yeah, definitely we could use that. Okay, next question is, would be possible to load dynamically QML views by loading them from memory? So this is, I think that this is a question not necessarily for me. Qt for MCU doesn't do dynamic QMLs because as far as I can answer that, because Qt for MCU translates QML into C++ files, and then actually use those C++ files to provide an application out of it, right? So I don't know how this might work. Okay, and the next question is the RPMSG implementation has any safety certifications? Not that I'm aware of. So so I think that if someone wants to actually certify this solution, it would have to go, the RPMSG and MCMGR would have to go through certification process as well. But this is, I think this is a question to NXP, and NXP can answer that better. Okay, so that's the last question. So if there, yeah.
Yeah, thank you. If there are any more questions, I guess you can send them directly to Bartosz or Qt at info@qt.io. But yeah, thank you so much for the informative session. As we close the session, please know that you can find the link to send us feedback or join the next live session via the thank you page. So www.qt.io/thankyousurvey. But yeah, thank you again, and please join our next sections through the live event pages. Thank you, Bartosz, and thanks everyone for joining.
Yeah, thanks.
Thank you. Bye.
Bye.